We're about to dive into one of the most fundamental and, let's be honest, one of the most mind-bending truths about our universe. It's a concept that tells us the solid world all around us, well, it's not quite what it seems.
Sounds crazy, right? Like something straight out of science fiction. But what if it's actually true? This isn't just some fun thought experiment. It's the key to understanding how reality itself works at the tiniest, most fundamental levels. So stick around because this gets wild. All right, to get our heads around this whole bowling ball as a wave thing, we've got to rewind the clock. We need to go back to a time when physics was staring down a deep, really troubling contradiction, a cosmic mystery that all centered on one simple thing: light. For literally centuries, physicists were in a huge debate. On one side, you had Team Newton. He was convinced light was made of tiny little particles, like microscopic bullets. And hey, that model worked great for explaining why light makes sharp shadows. But then you had Team Huygens, who argued that no, light is a wave, spreading out just like ripples on a pond. And that idea was perfect for explaining things like diffraction, how waves can kind of bend around corners. Classical physics just couldn't make them both fit. It was one or the other.
So what was the answer? Well, it turns out the resolution wasn't to pick a side. It was to accept a totally bizarre new reality. Somehow, light is both a particle and a wave at the same time. This is wave-particle duality, and it's a cornerstone of quantum mechanics. And here's the real kicker. This strange dual identity doesn't just apply to light. It applies to, well, everything. Okay, so this is where our main character walks on stage, a young physicist named Louis De Broglie, who in his PhD thesis, his PhD thesis drops an idea so bold, so elegant, it will completely change physics forever. See, De Broglie looked at this paradox, and instead of getting confused by it, he just embraced it. He decided to take this incredible leap of faith, a leap that would connect the world of energy and the world of matter in a way no one had ever imagined. Now, he didn't just pull this idea out of thin air, right? He was standing on the shoulders of giants. He was connecting the dots between two revolutionary ideas from two of the biggest names in the game, Max Planck and Albert Einstein. First up, you've got Max Planck. His big idea was that energy doesn't come in a smooth, continuous flow. Nope, it comes in these tiny, distinct little bundles, these packets that he called quanta. The energy of one of these packets is just its frequency times h, this super, super tiny number we call Planck's constant. This was really the first clue that waves had some kind of particle-like nature. Then, Einstein enters the picture. He takes Planck's idea and just sprints with it. He proposed that light itself is made of these energy packets. Let's call them photons. And here is the absolutely crucial part. He showed that these little particles of light still have a wave property, a wavelength. And that was the link. A particle property, momentum, was now directly tied to a wave property, wavelength. And this is where De Broglie has his aha moment. He looks at Einstein's formula for light, and he asks this beautiful, simple question you see right here. If a wave, like light, can have a particle property like momentum, why can't it work the other way around? Why can't a particle, like an electron, have a wave property like a wavelength? He basically bet that nature loves symmetry. He proposed that this rule wasn't special to light, it had to be universal. And boom, this is it. By simply rearranging that formula, he gives us this profound equation, the de Broglie wavelength. It says that the wavelength of any object is just that tiny number, Planck's constant, divided by its momentum. The key takeaway here? This isn't just about light anymore. Suddenly, everything that has momentum, from a tiny electron to you to an entire planet, has a wavelength. It is a universal property of matter. Just let that sink in for a second. It's an absolutely mind-blowing idea. But, in science, a beautiful theory is great, but it's not enough. Science demands proof, and that led to a huge problem. Yeah, think about it. How in the world are you supposed to design an experiment to see the ripple of one single, impossibly small electron? It seems like a total dead end, right? Well, two physicists over at Bell Labs were about to figure it out. Their setup was just pure genius. They took an electron gun and fired a beam of electrons at a crystal of nickel. Now, here's the clever part. The atoms inside that crystal are all lined up in this perfect, orderly grid. That grid acts like a tiny, tiny fence with very specific gaps. Now, if electrons were just little bullets, they'd bounce off all over the place randomly. But if they were actually waves, they would diffract and create a very specific, telltale pattern on the other side, a wave pattern. So they ran the experiment, and the results were just breathtaking. First, they used de Broglie's own formula to calculate what the wavelength should be for their electrons. The math said 0.165 nanometers. Then they looked at the actual pattern the electrons made in their experiment and used that data to calculate the wavelength that must have created it. And the number they got? You guessed it, almost exactly 0.165 nanometers. It was a perfect, dead-on match. You couldn't ask for better proof. It was the cinematic climax to a huge scientific mystery. The data was undeniable. De Broglie wasn't just dreaming this up. He was right. An electron, this thing we had always pictured as a tiny little ball, was, without a doubt, also a wave. So this discovery completely rewrote the rulebook of physics. But it also brings us right back to that first big question. If everything is a wave, why don't we see a bowling ball making ripples as it rolls down the lane? It all boils down to one thing: scale. As you can see here, an electron's wavelength, while itty-bitty, is still big enough to actually interact with the spaces between atoms. But now look at the baseball. Because it has so much more mass, its momentum is gigantic in comparison. When you plug that into de Broglie's equation, the wavelength you get is, well, it's so small it's almost meaningless. Trillions upon trillions of times smaller than a single proton. So yeah, the wave nature is there, but it's so ridiculously tiny that it's completely undetectable and has zero effect on our everyday world. You really can't overstate how huge this discovery was. This idea is the bedrock of all modern quantum physics. It led directly to things like the Heisenberg uncertainty principle, the idea that you can never know a particle's exact position and momentum at the same time. And this isn't just some abstract theory. It's the reason we have technology like the electron microscope, which lets us literally see atoms, and the transistors that power every computer on the planet. And maybe the most profound part is how it completely changed our philosophy of reality itself. It introduced the observer effect, this totally wild but proven idea that at the quantum level, reality is fuzzy until it's measured. The simple act of looking at a particle forces its wave of possibilities to collapse into one single outcome. It means we're not just passive observers watching the universe, we are active participants. So in the end, we live in a universe that's like a grand quantum symphony. Every single particle is humming with its own wave, all weaving together to create the reality we experience. It's so much stranger and so much more beautiful than we ever could have imagined. And it leaves you with a final question, right? Now that we know every particle is a wave, what other secrets are just waiting to be heard in that music?